Thank you. And thank you very much to the organizers for allowing me to present this work and for also putting together this wonderful workshop. I've learned a lot and also more importantly, I realized that there's a lot I need to learn. Um, so with no further ado, there's a lot we need to learn about active galactic nuclei and their hosts. And so they are how are they related to how galaxies evolve. So one of the fundamental questions of astronomy are why galaxies look the way they do. And this nice Hubble work made with Spitzer images of nearby galaxies illustrates one of our first attempts to piece together the look of the galaxy to its evolution. It was a wrong way of doing it, but it was our first try. Um, so not only do we care to understand the shape, the morphologies of galaxies and their stellar masses and other properties, but we also have been finding that most massive galaxies, actually all massive galaxies where we will had the sufficient resolution and sensitivity, have a massive black hole. And so the question then is if the universe abounds with massive black holes, where did they come from, when did they grow, and how did they grow? And I was very happy to hear this morning that this was a puzzle that also kept other people um, from sleeping. So in order to start answering those questions, one of the things astronomers do is plot x versus y and see a correlation. So when looking at the masses of the central supermassive black holes and the mass of the bulge galaxy, we found this correlation for the past 20 years. Points have been added, and the scatter has been limited. Specifically, what has been lowered is the scatter of observational uncertainties. So our measurements are getting better, but the scatter is not getting smaller. So that suggests that there is a physical reason for this scatter, and one way to explain it is through feedback, meaning that the processes that are associated with the AGN tend to insert energy and momentum into the host galaxy's interstellar medium, which may affect its properties and its star formation history. Therefore, star formation history, the size of the bulge that it will be able to make. So to achieve those great goals of figuring out where the black holes are, why are they correlated to the properties of their galaxies, and why do galaxies look the way they are, we just need to find a lot of them. And one particular missing parameter space that was covered by Spitzer were obscured AGN. And so Spitzer was particularly transformative in finding such galaxies, as was WISE that came after it, because it allowed us to look at the worm dust properties as shown here in this. Okay. Yes. So the color of the mid-infrared emission tracks with the energy of the radiation that is put in. One simple way to look at it, if you have a bunch of grains and the emission from the AGN will either ionize them, and so it will destroy some of the grains, and in especially the small ones, and also it will heat up the medium infrared continuum, and so that's what leads to this medium infrared selection technique for AGN. So when that's being done, and then a number of medium infrared selected AGN are being hundreds to thousands of medium infrared selected AGN are being found and followed up spectroscopically, what we find is that their evolution with redshift seems to differ. And in that sense, what it points to is that the processes that are being observed while you are observing an obscured AGN, so either a snapshot in time or the kind of AGN population that this is tracked evolves differently and may be triggered by different processes. So what future missions will do is, in particular, Roman is very exciting, very excited. I'm very excited about Roman for that. Is that it will allow us to follow down the morphologies and the properties of medium infrared selected AGN for dusty AGN with incredible numbers, so that we can generate the sufficient statistics to study their evolution as a function of redshift. So, okay, so they are, we see obscured AGN evolve differently, and we may think that this has to do something with their either the snapshot in time or their evolution altogether. And this fits nicely into this picture where gas-rich mergers, lead to a period of obscured growth for the supermassive black hole as well as the host galaxy. And once that AGN is able to either insert energy through jets, turbulence through the interstellar medium, it clears up a path toward the broadline region. And so we are able to observe broadline quasars, but at the same time, in that clearing process, it prevents the gas from making stars because the gas has been impacted by the AGN. So in this scenario, the AGN is obscured. Okay, well, that was not that, but that's okay. So in the previous slide was very obscured because it was of luminous infrared galaxies, nearby luminous infrared galaxies. And so those are, there are about 200 of them in the nearby universe, and they've been very well observed with Spitzer. And what we found in them was that the LIRGs with the higher contribution of AGN to the total infrared luminosity were also advanced stage mergers. And so this is in agreement with a picture that I mentioned before with the gas-rich mergers triggering AGN. However, if you look at other samples of either slightly or at a higher redshift, not of luminous infrared galaxies, but just of obscured AGN, the picture becomes more complicated. So in this work by Lambrides et al. 2021, the point of it is that the blue histogram that represents the AGN differs from the control sample, that is the orange histogram, in the nearby universe, but they are all on top of each other at a redshift greater than 1.1. So basically, the picture is more clear that in the nearby universe, you have a difference between the merger status of obscured and non-obscured AGN, but at higher redshift, it's more challenging to figure this out. So the explanation could be that there is a physical difference, or another simple, more observational point is that we may be missing lower luminosity AGN at high redshift. And this picture is supported that we're missing things. Is supported by the fact that if we go with Hubble for the brightest sources, the dust-ridden quasars, most of them appear to be mergers. But again, this is a sample of a few. And so what Roman, as we've heard this morning, one of the things that Roman will do for you is be able to provide a large statistical sample of obscured quasar, and not only with the imaging so that you can look at morphologies, but also I'm very excited about the slitless spectroscopy opportunities, which will allow you to get redshifts and maybe make some physical measurements of the properties of the gas and the host. So not only the future is bright for obscured AGN at high redshift for luminous big sources, but also we are finding, and this is a paper that appeared today on Astropy. No, sorry. So what JWST will do is provide us a way to look at more, is providing us with a way to look at morphologies at higher redshift. And what we seem to be finding is that it finds fewer mergers at certain levels than HST. So let me say that again. So basically for high mass, we get similar values of mergers. But when we look at lower masses, then at say Z equal to this cosmic noon where everything is supposed to have been growing very fast. JWST finds 50% disks while HST was finding 10% disks. So there can be a physical explanation in that some galaxies grow by other things, which we kind of knew. But again, this points to the need for more observations that will allow us to identify whether this is a sample selection or something different. So this was from today. We also finding black holes at lower masses, and we will follow them up to find what are their merger properties. But to understand how the gas, how the black holes are growing and how their hosts are being impacted, then we want to follow the gas. And one way to do that is with the mid-infrared. So on the plot on the left, it shows you the H2 properties versus the equivalent path of the 6.2 path. So basically, the top are star forming and the bottom are AGN-ish. And what we see is that the warm molecular gas in AGN is hotter than in non-AGN. And this was with a high statistical accuracy. Basically, all the galaxies, all the AGN that Spitzer observed. And so to follow the gas in more detail, especially for observe certain kinds of galaxies, is very exciting. In particularly, galaxies with multiple AGN. So one of my favorite galaxies is Markarian 266. It has 2 AGN. It has a loop that may be spilling stuff in the CGM. And it's something that we will be able to study more of with both JWST and Roman. So as mentioned, Roman will be very exciting for the obscured AGN because it will allow us to get morphologies and redshifts at the very redshifts where those populations of galaxies seem to evolve differently. And so I will end with some of the properties of Roman. There are others, there are synergies between Roman and many other missions. So the future is bright for obscured AGN, and I'll take questions.
Thank you very much. Any questions for Andreea?
Thank you for the talk. In terms of obscured AGNs, I guess a question that is, or any kind of AGN, a question there is like how much of it we are missing, or what fraction have we detected? So in the kind of the merger plots and other things that you were showing us, and I saw all of them had error bars, are those kind of accounted for from some
Yes.
luminosity function
Yes.
or something? Okay.
Yeah.
There's this amazing difference between HST and James Webb disk fractions at redshift 2. Do you think this is because of the way how disk galaxies are defined? Is it different wavelengths? Is it, yeah,
I think it is a question of better observations that allow us to track more of to find the smaller things and more of them easier. So but it's also the case, it must be also the case that some are not, just like not all AGN are being triggered by gas-rich mergers, not all big galaxies are formed by mergers.
Are there any questions from the Zoom? No? I have a quick one. So in this picture where the obscured AGN are sort of triggered by merger activity, I'm thinking about the relative timescales of the two and when you might be able to observe them being coincident. What are our expectations for the timescale of how long merger signatures last versus the evolution of the AGN?
That's an excellent question, and it is it is also a question slash explanation that we put in various papers I mean that we put when we discuss the differences. So the answer is we're not sure, but that may be why we're not seeing some of the strong correlation between mergers and black holes. But the thing is that you can trace those, the merger stages has been shown that you can trace them by various things. So for example, H1 is able to find gas-phase mergers by the clump type, like remnants, easier than, let's say, the infrared. So with SCA, we'll be able to probe different ways of different time snapshots for the mergers, and so maybe that will change our understanding.
Great. Let's thank Andrea again. And now I think we have Francisco.
Okay.
Take it away.
So I'm going to tell you about the flagship Galaxy Map catalog. There's a lot of material in the transparencies. I decided to put a lot or not remove them. So you won't, well, if you want to look at them after, they will be there, but I'm going to go pretty fast through them. So basically, as always, there are many people behind all these big endeavors. So here are the names. But basically, the idea is that, well, we focus these simulations just to respond to Euclid needs for a big simulations. And basically, Euclid is a struggle, well, and it's space missions, and that is going to take 15,000 square degrees of the sky, and it's going to use lensing and clustering for studying cosmology. And basically, the thing is that clustering is going to be done with a spectroscopy, a slitless spectroscopy. So the selection is done with emission lines. So, and then lensing, well, and the idea is that, and also for selecting the weak lensing samples, and there's going to be photometric redshifts just to do the tomographic analysis of weak lensing. No? And basically, so basically what we need to then have is, well, we need to have a good luminosity function of number count. So we need to have the proper densities. We also, if we want to do anything with photosees, we need good color distributions. If we select the samples for galaxy clustering with emission lines, we have to define pretty well the emission line fluxes. And then for lensing, we need sizes, shapes. We also have all the weak lensing properties. And then the other thing is that we have auto consistently from the same simulation, from lensing and clustering together. So whenever you do this now popular 3x2 point statistics, you are drawn from the same matter distribution for the clustering and the lensing. So basically, this was the dark matter was done at Zurich by Joachim Stadel and Doug Potter. Basically, there was the first attempt, the flagship 1 and the flagship 2. And in the flagship 2, well, Euclid is going to take a wide survey, 15,000 square degrees, and then a deep survey, 3 fields, 50 square degrees to go deeper. So, and there are been 2 simulations being developed. These are, as far as I know, this is the largest embodied simulation run today. There are very similar ones, but I think it's slightly lower than this one. So it's 4 trillion particles that is run in a large box, and that's the resolution in mass that we have it. So what do we want to do? So basically, the other thing is that from the embody simulation, and the output is relatively large. So I think if you have a snapshot of the dark matter is 112 terabytes. So it's hard to work with this amount of data. So basically the data is reduced to halo catalogs, and also the LightCon, as we cannot afford to have so many snapshots output to disk and then build um, the LightCon. The LightCon is built as the simulation is running, and then that has some disadvantages because you don't have as much information on the halos as you would like, but at least well, we can work with it. So basically, this is the information we have for the halos. And one of the things is, as there are no snapshots, we don't have merger trees, and that precludes from doing semi-analytics. And then also we build the lensing maps, projected mass density. And from that, basically, we want to go and get a galaxy catalog with a lot of properties for each galaxy. And well, how do we go from left to right? And you say, well, machine learning it. So that's what Paco does. But we took a different route. One of the things, the challenges is that, well, the halo catalog is 10 billion particle, 10 billion halos. So whatever you do, it has to be fast and efficient. So that's machine learning is built for that. But basically, when in the steps that we do, basically, whenever something takes more than 1 second for a million galaxies, it starts to be too much time. So things need to be efficient. And then the other thing is that, well, the parameter space that we're sampling is very large. So there are sometimes you don't have constraints and you have to extrapolate. And that's not so good for machine learning. So basically, the idea is that, well, the recipes that we are using, we were extrapolating from what we did for mice, and basically we have an HOD, abundance matching, and then some properties, distributions, and correlations, and everything. Mice, we run them in desktops. This is running a computer center with nice architecture and a lot of things. So this is kind of the pipeline, and basically we have an HOD, and basically the HOD is simply to force the resolution to the very limit. Because in a halo, if we just count what, well, we go to very low number of particles to define a halo, and then you don't have any substructure, or if you count the subhalos that you can measure in a halo, there aren't enough subhalos to be complete to the limits that we want. So basically the HOD is a way of pushing your resolution to lower masses. And then we do abundance matching. We need to define luminosity function as input. We assume halos profiles, and then we do several things here for the halo properties. And the other step that is very crucial is how you go from the things that we get with colors and luminosities to SEDs. And that's a delicate step where machine learning, I think, can play a very important role. And so this is just plot. So basically you have your halo mass function. And the thing we do with the HOD is that instead of halos, we go to galaxies. So how many galaxies are at a given mass threshold? Then you have your luminosity function, and then you do abundance matching, and you have a relation between your halo mass and luminosity. But then if you want to conserve the clustering, you need to account for a scatter. Otherwise, if you do magnitude limited samples, the clustering won't be as observed. So you need to account for a scatter. So basically, we unscatter these luminosity functions so that whenever we put a scatter, we recover the luminosity function. And this is the abundance matching of the unscattered things. So, and then this is what we get out. And basically, the idea is with centrals and galaxies, because we are always working with centrals and galaxies. And well, things look fine from redshift basically 0 to redshift 2.5. So the other thing is that we, in order to apply different, how we populate satellites and how many satellites we have, so the parameters of your HOD depend, we made them depend on color. So the clustering also has dependence on color. And basically, we parameterize things with basically 3 populations. And this is at low redshift. This is a color magnitude diagram. So if you, this is just well, integrating up to -18. So it's integrating on that axis. And basically, we have 3 populations: red things, blue things, and things in between. And we work with that. And this is the money plot, where there's a lot of information here that is important on how the resulting clustering behaves as a function of color. So I don't have time to go. Oh, wow. This is the number counts that we get, and they look pretty good. In the H band, we are a little bit too high, too bright, but this is how we populate clusters. This is a relatively fairly massive cluster at low redshift, and this has like 1,800 satellites. So, so we go very faint into the luminosity function. This is, we put some color segregation in the distribution of objects. This is the velocities. We have an anisotropic model for the velocities. These are the distributions of some colors as a function of redshift, and compared to Cosmos, and they look fairly reasonable. As I said, in the near infrared, we are a little bit too red, too bright, but color diagrams look reasonable. Then we put shapes and sizes, and basically we get constraints from HST data and candles, and basically we reproduce the scale lengths. This is basically, we assume that everything is either a single Sersic component, that is basically a bulge, or although it doesn't need to be N4 for the Sersic index, or 2 Sersic components. And basically, most of the things are 2 Sersics, and then this is the ones that have bulge fraction. One is the ones that are just 1 Sersic. It's not N4, and then for the bulges, it depends on the HST analysis. Different people work with different assumptions on how they deconvolve things between, and so we are, in the end, we are kind of in between of what candles does for Sertis indices and an analysis of the Brits that had a different way of separating components. And then there's distributions of scale lengths and ellipticities and well, a lot of things. So going to stellar masses, this is just a stellar mass versus magnitude. So things look like Cosmos, more or less. This is stellar mass metallicity. It's fine at low redshift. At higher redshift, the constraints are more difficult, so it's kind of a guess. This is another thing that is important, is how we simulate the emission lines. And basically, we go from the SED that we assign with the UV, we go to a star formation rate and H alpha, but then we recalibrate to models. And here is a plot of what comes out straight from the simulation, that is the blue, and then the 2 models that we are simulating, that is the Posetti et al. Model 1 and Model 3. And this is, if we cut at the flux limit of Euclid, that is, this is the N offset that we get. And this is what Euclid is expected to have as a sample. No? And basically, with the Grism that we have, we will only observe from, detect H alpha from 0.9 to 1.8. This is the BPT diagram. Nitrogen 2 H alpha, oxygen 3 H beta, and that's with sulfur 2. And this is what we get at low redshift. And this is for comparison with the Sloan. And one thing that you will see is that we don't have AGN. So, and this is, well, other statistics of clustering as a function of redshift. This is in projected slices and lensing in the dark matter and in the galaxies at different redshifts. We have shear 2-point correlation function, galaxy-galaxy lensing, and their magnification, and things look as expected from theory. And then the other thing is that we have made an attempt to put intrinsic alignments into the lensing, so that our shears have also a contribution of intrinsic alignments, because this is something that the lensing community is very worried about as a systematic. And so in the end, we cut our catalog at age 26, and we have 3.3 billion galaxies in the catalog that we serve from our portal. It's 1 octane of the sky. Each galaxy has 380 properties. So it's a huge database. I think it's around 2 terabytes what we are serving from the. And then when we cut with H alpha, it's basically, we end up with 30 million or 60 million, depending on whether we cut in one model or the other. So what are the next steps? Now we are in the process of producing the deep, that is basically as much a smaller area, but going to higher redshift. And then we want to extend to redshift 10, and then we will lack observational constraints. With the new data of JWST, we'll have some, but so we'll have to see what we do there. The other thing is that we have ideas of how to introduce AGN. There are groups working on that. And then, well, I think I didn't have another one. Okay. And then there are steps when I think we can get probably results using machine learning techniques, and I think that's kind of a reason why I'm here, to see how we can change one of the things that we do to try to do it in a different way that can be probably more efficient. And that's all. Thank you.
Okay, thank you, Francisco. We're running a little short on time, but I think we could squeeze in one question, if there are any. Yep, go ahead.
If I understand correctly, so you use sham basically when you have enough subhalos and you class them, and you use the H of D when basically the halo mass is too low. If I understand what you.
No, we just use the halos, and then we populate all the subhalos are from the HOD.
All the subhalos are from the HOD.
Yep.
So, okay, maybe I can talk later.
Well, the halo finder has some halos, and we could use them, but it's the way we do it is not straightforward to do it in an efficient way. So I have done it for when you have like 10 to the 6, 10 to the 7, to 10 to the 8. When do you go to 10 to the 10? But the thing is something that we want to do now is with this flagship and to try to do that. The other thing is that our Halo provider, that is Zurich people, they haven't provided us exactly the catalogs that we wanted to start playing with that and do it. But in the end, the idea is that instead of doing as we have basically, and when we populate the satellites, we have just NFWs. They are triaxial, but they are NFWs. If we have information of the subhalos and particles in the halos themselves, then we can use that information to put the galaxies within the halos.
All right, thank you very much. Let's thank Francisco one more time. And now I think we have a remote tutorial. Let's see. Hopefully Toby's on the Zoom. Aha.
Hello, sorry, there's too many screens.
All right, well, now that you're here with us, please, Toby, go ahead and take it away.
Thank you. Could you remind me how long I have? Or basically, what time do you want to finish?
Let's see. I think noon, so about half an hour.
Okay, cool.
Including questions. So let's say 20 minutes.
All right, let's do that. Great, this is fantastic. Thank you very much for inviting me. I will just share my screen, mainly so I don't have to look at myself on Zoom. Let's go the full desktop. Hopefully you can see this. Okay, so I'm just going to give like 3 slides to kind of orientate everyone right at the start. So I'm going to give a quick demo of what is called the CANFAR science platform, and CANFAR just stands for the Canadian Advanced Network for Astronomical Research. But this is not meant to be sort of a lobbying attempt for you all to go and get CANFAR accounts. My main kind of point I want to convey is the power of science platforms in general for you and your group to do your science. So why am I so keen on these online science platforms? I think it's pretty obvious now that many of us are both currently facing barriers to doing science, and also those barriers are going to grow in the future. So kind of the undergrads coming through now, and even sort of the people coming after that, the future PhD students and postdocs doing the majority of the science, are really going to face these huge data volumes from the next generation of facilities and simulations that just they can't be dealt with local computing, and even they push the bounds of what can be addressed with kind of a cluster at different universities and so on. Of course, as kind of data sets and facilities grow, so do the collaborations to do the science. So, I mean, for example, I lead a collaboration that is not particularly big, but we're still 40 people spread all around the world. And so it immediately, as soon as you go to that kind of collaboration, you run into issues around data management, moving large amounts of data around the world, giving people permissions to access data and products, collaborating on analyses, sharing code, all these types of things are made more challenging by the fact that we have these distributed teams. And then, of course, we've had weeks now of kind of a really nice overview of some of the software that people are using in galaxy evolution, analysis and astronomy in general. And while it's fantastic software, the kind of taken as a whole, the landscape is growing ever more complex. And so these software packages have hundreds of dependencies. Installing them requires kind of technical understanding, as does sharing them, occasionally running them. And of course, all of this adds into kind of this question of reproducibility, which is key. I mean, we teach our children that science should be reproducible. And yet, honestly, I would argue that these 3 top points have effectively rendered much of the analysis that you see on say, the archive unreproducible. You might get the same result or in the same sense, but the actual steps of the analyses are very difficult to pull off. And I'm sure you've faced that with, you know, your PhD students going through when you're trying to recreate somebody's result. Okay, so I'm just going to jump straight to a user's view of the CANFAR science platform. And honestly, this could be a user's view of most science platforms. There's a couple of tweaks and let's say features that we have with CANFAR that I think make it particularly powerful for the kind of for overcoming those barriers that I outlined on that first slide. So the first one I want to mention is customizable software and tools. So really what I should have just put here is software containers, if you know what this is. So essentially software containers are just ways of really efficiently packaging up software and all its dependencies so it can be deployed on different hardware. And what you can do there is if you allow users and groups to bring their own and modify their own containers, you basically inherit all the advantages of speed and flexibility that software containers have. You inherit that with your science platform, and I think is a really powerful feature for allowing a platform to organically grow in kind of the communities that it serves and how it kind of tackles different problems. And then, of course, the other one, which I think is a bit more common, is scalable compute and storage resources is key. So to give you kind of an example, if you have a big telescope program, you often end up needing really intensive compute resources at the start when you're going from the raw data to the science-ready data products. And then once you're into those data products, you know, it cools down a little bit. So being able to scale up and crucially scale down your resource request is really key for efficiently managing groups and many different projects and so on. Okay. So this is my takeaway from the whole talk. You can, if you want to tune out and just take something away, please let it be this, is that science platforms are a flexible and efficient solution to many of the research challenges that we face. I'm not bothered which platform you pick, just pick the one that suits your needs best, but they all require a really engaged user community to drive development, ask for features, report bugs, all this stuff that usual, you know, software projects need as well. And then just in terms of something I hope we all as a community keep front of mind when we're developing these platforms is that flexibility and reproducibility should be a key goal, a pillar of all the work that we do. Okay, so unless there are any questions on that, I'll jump straight into a demo. All right.
Anybody have any questions or comments? Doesn't look like it.
Great.
All right.
Okay, so this will be pretty quick. And I think that's a good thing because, you know, if it takes me an hour to talk you through how you get started on a science platform, something's gone wrong with the user design and user experience. So, you know, simple is kind. Okay, so for us, we go to this website, camfire.net. This is the homepage. We click Science Portal. You need an account, you need the authorization and authentication to work for you. And then this is it. This is all my kind of compute sessions on the science platform. Currently, we limit it to 3. This is purely based on resource, right? We don't want people coming in and just requesting a dozen different sessions, hogging up a load of resources that other people then can't use easily. So we want people to be judicious in their use of resources that are ultimately shared. And you get this kind of set of drop-down menus here where you can select the different type of session that you want on the platform, the different container. So this is just the software container that you want to deploy that has your set of software in it, or you can use an off-the-shelf one that we built for you. Some name, you know, call it test, whatever, call it something. And then scalable resources. You can see we go up here to 192 gigs of memory, and that is per core, and then we can go to kind of 16 cores. So you're already getting really huge resource requests, and this is just the kind of off-the-shelf version. If you need more, I can mention about, you know, you can get more. But so we're already being really flexible in our resource, or you can request something that's, you know, kind of comparable to a fairly low-level MacBook or something like this. Now, the first session here that I have is a Jupyter Lab session. I've actually already opened it, and you're all familiar, I'm sure now, with Jupyter Lab. I mean, it's becoming kind of really wide widely used in astronomy. I think it's fantastic. We're doing all the tutorials at this conference using notebooks and so on. So I'm just going to park that for now because I think you know it and understand its functionality. And I want to highlight where the Camphor Science platform in particular is doing really good things because it allows user contributed software and session containers to be deployed. So for example, fundamentally, really, I'm a radio astronomer, although I don't like to admit it. And so something we have in radio astronomy is Carter, which is for visualization. I think maybe many of you use it. It's a super nice tool. So we kind of put together a Carter container, and we can request it and then deploy whatever version of Carter we want, give it a name and flexible kind of resources. Say if I'm dealing with like a 50 gigabyte cube, I'm going to want a lot of memory. And then that, if you click launch, that would then launch this session that I already have actually open here handily. Here's one I made earlier. And you see here instantly that I have kind of two sets of data, some HST imaging and then some ALMA imaging of the same galaxy. And it looks all nice. I can go away and do my analysis straight away. And the thing that is really powerful about this mode of working is that all of these sessions are looking at the same file system. So I can, make a moment map in Carter or a spectrum or whatever, do my analysis, and then go away and load it directly. I can save it from the file menu, save image type of thing, and then come and load it back in my notebook and carry on with my analysis. So you end up with this kind of end-to-end analysis platform, let's say, that goes right from downloading data directly from the telescope through to producing that plot that goes in the paper. Okay, and then the other thing I wanted to show here is that I'm also part of a team that is kind of in the process of planning for a new telescope called Castor, think like Hubble in the UV, basically. And we needed an exposure time calculator, and one of our students put together this really nice software container that runs on a platform and is an exposure time calculator. So all our Castor team have access to this science platform. Therefore, they all have access to this exposure time calculator, and any updates and so on are just pushed to this software container. And so everyone gets the version, like the latest version of the ETC. Okay, so we have, we are running low on time. So I did actually want to give one demo, since I have it, of a machine learning kind of tool that I think will be useful. And I'm going to try and do it in 5 minutes. So it's really just going to be a highlights taste test. So I was kind of inspired by John's tutorial, predicting galaxy metallicities. He was doing it from imaging. Well, you can also kind of conceptually do the same thing from tabular data. So this is just the kind of basic use case I'm showing here, just predicting galaxy metallicity. But I'm using this package called PyCarray. And maybe some of you are familiar with this, but I think it's fantastic tool. So, I'm an astronomer. I like physics. I'm not a computer scientist. I like ML kind of from a nerdy point of view, but I am not an ML expert, and kind of the ML workflow is still a bit laborious for me. PyCarray packages up that entire workflow into this, what they call a low-code solution, where I can compare and contrast models on my data and basically go end-to-end. So from the data preparation right the way through to the model selection, as well as providing really good logging. So that helps with the reproducibility. And it has all these different modules. So it'll do regression, classification, time series. I know people are using this with telescopes now to figure out when to open and close the domes and stuff. natural language processing, association rule stuff. So there's a lot going on in the package. And essentially what the demo is that I've prepared and I've shared on Slack is if we take just a subset of SDSS galaxies for which metallicities are measured. In this subset, there are 12,000 galaxies for which we have metallicity measurements, and then 17,000 where we don't. Okay, and we plot the galaxies for which we have metallicity and stellar mass measurements. We get the beautiful mass metallicity relationship that we know and love. And then you're straight, once you have that data, you're straight into the kind of the machine learning workflow via this command setup. And so you give it just the pandas data frame, you set your target, your target feature. Do you want to log the experiment and some file types? And I just tell it to ignore the ID, because obviously I know ID has no predictive power here. Okay, now this here is the coolest thing in the whole package, I think. If you just take one thing away, it's this. Okay, there is this function here, compare models. And once I've done my data setup, let's see if I can kind of run this out of order. I'm going to just run compare models. Come on, work. Usually it takes no time at all. So of course now it's taking ages, but it'll fly through running fitting and training on 20 different models, and then provide you the scores, the key metrics for looking at those models. And it's a great way of narrowing down, particularly if, like me, you don't have an encyclopedic knowledge of all the different ML models that are available and their particular use cases. Here is just, I thought it might be interesting for you to see a list of all the different regression models they have in the package. When I ran it before and it worked, here we go. Just took a while to kick in. So you see it has this nice kind of on the fly updating of the GUI. And then I'll just let that kind of tick away, but it will eventually kind of show me it'll rank them on how well they perform based on how I tell it to rank. So I think the default is R2 if I'm not mistaken. Anyway, so that ranking went through, and the cat boost regressor came out on top. So I just picked it for this one. I also like light gradient boosting machines, so I use this one as well. We go through, we make a couple of models, and then you can see it's really like simple API. And then it will also provide you the analysis plot, not the analysis plots, but the kind of the plots required for assessing how well your model is performing. You have this kind of nice interactive GUI that probably isn't working because the other cell is running. But anyway, the point being is that you can automate this end-to-end workflow for ML with PyCarray. I think it's really powerful. It's what, for example, when I have students, I put them onto this straight away. And I'll probably stop there so we have like 5 minutes for questions or so.
Awesome. Thank you so much. Questions for Toby? Yeah, go ahead.
Yeah, a few questions on the platform.
Mm-hmm.
Is that running on AWS or is it a?
No, we have it could be. So we have Compute Canada, which provides it's like essentially a cloud provider in Canada. And no, we don't run it on AWS because it's a price thing more than anything, but it is Kubernetes. So anything, basically you could run it on any commercial cloud, ideally. I mean, we've done some tests on this and the setup is not kind of completely seamless at the moment, but because it's a Kubernetes kind of based system, you could deploy anywhere, ideally. Just to kind of expand on that a little bit, actually, what I think one of the most powerful potential avenues for all of these platforms is this thing called federation. So the idea being that the platform, say we access you in the US and me in Canada, that we're accessing is the same to the user. It's completely transparent, but you would bring your own like community resources, for example. So you might, you know, at the CCA, you might want to run on AWS and we run on Compute Canada, and it just knows based on your ANA, like your authentication, where you're going to allocate those resources.
Thank you for the tutorial, Toby. I had a couple of questions. The first is, I'm trying to think about this tool in like current terms. So would you say this is like similar to, for example, open on demand that many local compute like HPCs run? And the second question is, let's say one of the challenges, I guess, as we move more into cloud computing is like people are now getting these grants of AWS credits or whatever, cloud credits. And one of the challenges is setting up on these platforms usually takes a lot of time. So could there be a model where, let's say I'm using this science platform and I could bring my own AWS nodes or any cloud compute nodes to it somehow? Is that possible some way?
Yeah, I'm going to address that second question first, because I didn't quite follow the first one. But for the second one, yeah, that's this federation idea. Now, the challenge is there. My understanding is that the technical challenge is, you know, it's a kind of a solved issue from the technical point of view. And the answer is yes. You should be able to say, I, as even an individual researcher, can bring my own cloud credits on commercial cloud and deploy that. And I think that's where we're going and how, yeah. And I think it's the future of these types of platforms. The issue is it really becomes political. It's a lot harder of a political kind of problem to solve. For example, you have, say, the Canadian government funding development of a science platform that is then paying Amazon. It is tricky. So, and that I'm afraid is above my pay grade. I missed that first question.
It's I can message you on Slack maybe.
Okay.
Okay, I thought I saw someone over here, but maybe I'm imagining it. All right, go ahead.
One more question on reproducibility. So I wonder if you've looked at, in some sense, workflow reproducibility beyond just saving notebooks. I've been looking at data lad as one of the possibilities for that, but I'm interested in other.
I like the idea, and we have not managed to do this, but I would love the idea of something like Binder, you know, where you do your analysis on the platform, and then ideally in a few steps or one step, you package that up into a container, including with the notebooks and everything, and the data if you can. And then that goes in as a URL, is hosted somewhere and goes into a paper as a URL. And then at that point, the student or the person who wants to reproduce the published analysis clicks the link, takes them to either the science platform or something like Binder, and they can go from there.
All right, we have just enough time for one more question, if there is any. Nope. All right. Well, thank you so much, Toby. This was really interesting and thought-provoking. Let's thank him one more time.